So, Fermi theory of beta decay we had done, and essentially it has got a nuclear matrix element MIF. You have this MIF square, and this is psi daughter, and essentially it is psi electron and psi neutron also, neutrino, and then you have this whatever interaction Hamiltonian, and here it is the parent. So, this is that matrix element square. This is one factor, but in Fermi theory what we had discussed, this only depends on the nuclear wave functions, because these two things we had taken as constants, 1 over root v, 1 over root v, neglecting all those higher order term in p dot r by h cross. And so, the energy dependence comes from that dn def, and we worked out that the number of electrons in momentum range p to p plus dp, if this we work out, this turns out to be some constant times Pe square, P nu square, then d Pe, right. So, that is the Np dp, and then we bring this factor which depends on z number of the daughter and the kinetic energy or momentum. So, this is that F factor, it takes care of the Coulomb interaction between the outgoing electron positron and the daughter. So, this is how that this is all electron. This is the momentum distribution. If you plot momentum as a function of the number of electrons as a function of its momentum p, the value of magnitude of the momentum, then you will have this kind of relation. In terms of kinetic energy, we can also do it in terms of kinetic energy. So, Nk dk, corresponding Nk dk, and when you put all these values in Fermi theory, it turns out to be some constant times, then you had a factor k plus 2 mc square, half of it, then you had a factor k plus mec square, and then you had a factor q minus k and square of this dk. So, this Nk versus k we try to calculate, and of course, this F factor, and match with the experimental shape. So, qualitatively we showed that it works, but if you want to make a quantitative comparison between the data and these this expression, better way to look at the agreement is to linearize this. You remember this shape is it's some kind of inverted parabola like. So, that is in that shape also one can compare, but if it can be written in terms of variables where the dependence is linear, then any deviation from that linearity is easy to observe. So, that can be done if I take this expression here, and dp is of course common. So, if I write Np here, p is for electron momentum, and then divided by this p square. So, this is p square and divided by this f also. So, f here. So, this quantity will be proportional to p nu square. So, you take square root of this quantity will be proportional to p nu, and in the approximation that rest mass energy of this neutrino is negligible, is 0. This energy of neutrino is p nu times c, and energy of neutrino is total energy available minus kinetic energy of electron. So, that is this, and hence this is proportional to. So, this is proportional to p nu, and p nu is proportional to q minus k, c is constant. So, q minus k. So, if this quantity is plotted against k, so kinetic energy on the horizontal axis and this quantity square root of n p by p square f on the y axis. So, this plot will be a straight line and with some kind of negative slope. So, that constant term is there. So, that should be a straight line, and any if it deviates from straight line shape, then you know that the Fermi expression is not good for that particular decay. So, I will show you two representative graphs of two different decays, and in one case you will see that this plot is quite linear, and in the other case you will see that it is not. This is generally known as Fermi Curie plot. So, there is a standard way to check whether this decay can be described in terms of this Fermi theory, in terms of this Fermi expression, or there are deviations. So, look at the screen and I will give you some data from old papers. This is from this DC Camp and LM Langer. This is Physical Review 129, volume number 129 and 1963 paper, and this side is that function n by p square and f square root of that. This is on this y axis. It is written here, but maybe letter size is small. So, this quantity is on the y axis, and on this side it is kinetic energy plus the rest mass energy of the electron. So, it is including that, and the in units of the rest mass energy itself. So, essentially it is against k. So, one can see that it is a very nice straight line except at the low energies, and this low energy deviation is not because any theoretical deviations, but this is experimental thing. It is a scattering of these beta particles inside the radioactive nucleus. At low energies that scattering is effective, and because of that this is deviating. At higher energies this scattering inside the source material is not very effective, and you get this very nice straight line. So, this is a very good agreement with the theory. So, this is one representative class of beta decays in which if you plot this Fermi Curie plot, if you construct this, the agreement is very good. It is a straight line, very good straight line. When you plot this square root of n by p square f as a function of kinetic energy. So, this is one example, it is one class of material. There are many more beta decays which just goes like this. So, Fermi expression is very good for that. Now, another graph that I want to show you is this. This is taken from this paper Langer and Price, Physical Review 75. This is 1949 paper, and here is the same plot here, that square root of n by p square f is a Fermi Curie plot, and you can see very clearly that it is not at all a straight line. You can see this is the curve, and this curve you can see you have convex upward, here concave upward, here it is concave upward, here it is convex upward. So, it deviates quite a bit from this curve. This is again a class of beta decays. There are a group of beta decays. There are many beta decay schemes which do not fit into a linear plot when one constructs this Fermi Curie plot. So, these two. So, where is the difference and how do we account for that? So, let us talk more on this on the board. I will need all these things, but I will do it again. Now, the agreement, the curve that was agreeing was for this particular decay 66 gallium, and this is 31, proton number is 31, this going to 66 zinc where proton number is 30 and proton is decreasing. So, it is converting into neutron. So, this is the kind of decay. So, here Fermi expression matches quite well with experiments. If you look at the spin parity of these nuclei, the parent nucleus and the daughter nucleus, this is a 0 plus state and this is also a 0 plus state. The second curve that I showed where it did not agree well was yttrium 91 here and 39 here proton number, and this decays to zirconium 38 and 91, and here also you will have positron and neutrino. Now, the spin parity of this parent nucleus yttrium 91 is half minus. So, nuclear spin is half, capital I, which we denote nuclear spin, total angular momentum of the nucleus, and the parity is negative. Whereas, if we go for this daughter nucleus zirconium 38, here the spin is 5/2 and parity is positive, and here Fermi expression does not match well. With experiments. Okay. So, there should be an essential physics difference between this and this, and that difference comes from the angular momentum parity. That is why we have mentioned all these parity things. So, if we look at the angular momentum and parity in these beta decays, you have this I pi of parent to start with, and then in the product you have I pi for the daughter, and then I pi for or spin angular momentum for or the total angular momentum for electron and of electron, and electron means electron or positron, and similarly neutrino means neutrino or antineutrino, whatever is the case. So, these outgoing particles can also carry angular momentum, and that makes all the difference. Now, this particular class 0 plus to 0 plus, there are other decays also in which the angular momentum taken away is 0. Okay. So, when we write this psi e as 1 over root v p dot r over h cross and then higher terms, and we retain only 1 in deriving the Fermi expression, we retained only 1. So, this essentially means that we are taking the wave function at the origin. In this, if I put r equal to 0, I will just get this 1. So, that means the electron neutrino, they are created at the center of this parent nucleus, and from there they are coming out. So, in that case, with respect to this daughter nucleus, the angular momentum, orbital angular momentum of these particles will be 0. So, the underlying approximation, the approximation that we did for Fermi expression by taking these electron and neutrino wave functions to be a constant, essentially we have committed that the orbital angular momentum of these outgoing particles with respect to the daughter nucleus is 0. So, the L for outgoing particles is 0. But then these two particles are fermions, they have a spin quantum number and both are spin half particles. So, electron and neutrino they have half and half spin angular momentum, and that can combine to half plus half can combine to 0 or 1, half and half it can combine to 0 or 1. So, S the spin quantum number that is of this these two particles electron antineutrino or positron neutrino, that can be 0 or that can be 1. So, if L is 0 and S is 0, then J is 0 for the outgoing particles. So, you have this parent nucleus having some spin, some angular momentum, total angular momentum, daughter nucleus and the outgoing particles, and if this is 0, if this J is 0, then you should have a parent nucleus I same as daughter nucleus I, and the parity, that parity will be governed by this L. So, if these outgoing particles have 0 orbital angular momentum, then there will not be a change in parity. So, there are two conditions you can do. One is this L equal to 0, S equal to 0 and J equal to 0. If that be the case, if the particles are going with orbital angular momentum 0 and their spins are combined, half and half are combining to 0, then this J will be 0, and this will lead to delta I equal to 0 and no change in parity. So, delta pi change in parity no, right. So, these transitions where orbital angular momentum of the outgoing particles is 0 and the spin angular momentum combine to S equal to 0, these transitions are known as allowed Fermi transitions. In fact, there are two parts, one part is allowed and other part is this Fermi transition, and these two correspond to allowed corresponds to L equal to 0. So, allowed corresponds to L is equal to 0. If in a beta decay the orbital angular momentum carried away by these outgoing particles is 0, those transitions are named allowed transitions. It is a technical name, do not take the dictionary meaning of allowed. The probability is high, the contribution is high if it is present, that is why somewhat close to the meaning, but not exactly. So, these are named as, termed as allowed transitions, and Fermi transitions is S is equal to 0. So, if the spin angular momentum of the two outgoing particles combine to S equal to 0, that is known as Fermi transition, and both of them are here in this case. If L is equal to 0 and S equal to 0, that is known as allowed Fermi transition. The other possibility where S is 1, so S can also be 1. So, if L is equal to 0 and S equal to 1, in that case J will be 1. And then taking this, that parent nucleus I, and then here after the decay is daughter nucleus I and then this J. So, the change from this angular momentum to this angular momentum will be can be 1 unit or 0 units, right, because if you have this I p and this should be or in vector this is I d plus 1. So, the value of I p can be I d plus 1 or I d plus 0 or I d plus minus 1. So, all these three possibilities are there. For example, if this I d is like let us say 2, then 2 and 1, this can give you 3, this can give you 2, this can give you 1. So, I p and I d differ by 1 unit. If the initially if this is 2, this can be 3, 2 or 1. So, it can differ by 1 unit or it can differ by 0 unit. So, in this case, if this is the case, in this case you will have delta I can be 0 or plus 1 or minus 1 and delta pi of course no, because delta pi is depending on the orbital angular momentum, and if the orbital angular momentum is 0, then minus 1 to the power 0 is plus 1. So, no change in parity. So, these are allowed transitions, these two cases are allowed transitions. So, this is allowed because L is equal to 0 and but capital S is 1. The spins of these outgoing particles are now combining to S is equal to 1, which we say parallel spins. So, here S equal to 0, sometimes it is called anti-parallel spin, and this is S is equal to 1. So, it is called parallel spins. In this case, it is gamma Taylor transition. So, these are the names, right. So, when S is equal to 1, the spin angular momentum of the two outgoing particles that combine to 1, those transitions are known gamma Taylor transitions, and if the orbital angular momentum of the outgoing two particles is 0, that is known as allowed transitions. So, it is allowed gamma Taylor, this is allowed Fermi. So, our expression that is derived using Fermi theory, it is essentially for allowed transitions, and all those beta decays which decay through these selections rules, these parity and spin angular momentum changes, they will in general conform to that expression. Now, if this L is not equal to 0, first let me give an estimate. What is the probability, what is the chance that L is not 0, L is 1 or L is 2 or L is 3 or more. So, if I take that classical view, you have a nucleus, assume it to be a sphere of radius r, and then the electron is coming out with some momentum P e, and this is the distance, perpendicular distance, right, from the center, this is the perpendicular distance r. The angular momentum in classical mechanics, angular momentum magnitude would be this linear momentum times this distance. So, P e times r. So, maximum angular momentum, let us look at maximum angular momentum. This electron or neutrino is to be created inside the nucleus and then it will come out in some direction. So, maximum will be when it is created close to the surface and comes out in a direction which is perpendicular to the radius joining radius joining that location where it is created, and that is P into R. Now, typically beta particle kinetic energy will be around, say, in mega electron volt range. So, let us make calculations for kinetic energy equal to 1 MeV. Typical. So, if this be the kinetic energy, what will be linear momentum for electron, let us say. So, for electron, since the rest mass energy is only 0.511 keV, so you have to use that relativistic expression P square C square plus m E square C4, this is the total energy, and this total energy is equal to rest mass energy times plus the kinetic energy. Okay. So, I need this P with K is equal to 1 MeV. We will do all rough calculations. So, let me write P square C square plus m E square C4. So, it is square of the rest mass energy, and rest mass energy is 0.5 MeV. So, square of that. So, everything will be in MeV. So, this is MeV square. Okay, let me write MeV square. Units also let us carry, and I have already squared it. So, here also you will have to square. So, MEC square is 0.5 and K is 1 MeV I am taking. So, it is 1.5 square MeV square. Okay. Just making an estimate what should be the maximum angular momentum, so that we know whether L equal to 1, 2, 3 or how probable they are. So, taking K equal to 1 MeV and using this expression, we have this result. So, what is P square C square then? P square C square is equal to 1.5 square will be 2.25 and 0.5 square will be 0.25. So, when you subtract, it will be 2. So, it is 2 MeV square. That tells that P square is these many MeV square by C square. So, square root of that about 1.5 MeV by C. Okay. So, the magnitude of linear momentum of this electron with kinetic energy 1 MeV will be 1.4 MeV by C. This is momentum unit MeV by C, often used in nuclear physics or high energy physics. So, maximum angular momentum is P into R. So, this maximum angular momentum is 1.4 MeV by C, and into R, typically take R is equal to say some 5-6 femtometers. So, let us say 5 femtometers, depends on the size. You know, nuclear sizes are around so 4, 5, 6 heavy nuclei 7, 8 femtometers, light nuclei 3, 4 femtometers. So, this is approximately 7 MeV Fm by C. Now, if I put this magnitude as L plus 1 h cross square root of that. Quantum mechanically, this is the angular momentum square. So, take square root of that. That is the, this is to be compared with angular momentum magnitude. So, this is equal to 7 MeV Fm by C. This h cross you can take here, and then square root of L plus 1 is equal to 7 by h cross C here, MeV Fm here, and h cross C, this is approximately 200 MeVFM. So, this would be approximately 1 by 30, 1 by 30, no units, which will be 0.03, something like 0.03. And if you try to get L from here, so L into L plus 1 will be square of that. Okay. So, if you try to get L from here, that L is going to be very small as compared to 1. So, it is quite unlikely or much less probable for these electrons, neutrinos to take away a orbital angular momentum more than L equal to 0. So, when this L equal to 0 is possible, that will be the most prominent mode. But then there are some cases where beta decay is possible between the parent state and the daughter state, and it is such that this allowed transition is actually not allowed, right. So, the first allowed is the technical name and second allowed is the dictionary word. So, the allowed transition, technical name, L equal to 0 transition is not allowed. That is, in some cases it is possible if this nuclear matrix element, for example, vanishes in this approximation, and in that case the whole probability becomes 0. So, L equal to 0 thing is not possible. Or for example, you have a parent state where parity is positive and you have the daughter state where parity is negative. Beta decay is energetically possible. If it beta decays, the total energy is reduced. So, that beta decay is energetically possible and favorable, but then the parity here is plus, here is negative, or it is opposite. So, if the parity changes, in that case you cannot have this L equal to 0 transition. This is actually not allowed. So, in that case, this whatever small probability of higher L values, that will come into picture and the beta decay will take place through those mechanisms. Now, these decays for which L is greater than 0, where L is the orbital angular momentum taken away by the outgoing particles. So, if L is not equal to 0 and beta decay takes place, those beta decays are known as forbidden decays. Once again, it is a technical name, forbidden decays. Okay. Do not go by dictionary meaning, they are not actually forbidden, they are less probable if this allowed transitions are possible, but if allowed transitions are not possible, then these are the modes of beta decay, and you have this. Then if L is equal to 1, you call it first forbidden, if L is equal to 2, you call it second forbidden, and so on. L is equal to 3, you call it third forbidden, and so on. So, in place of allowed, now you have forbidden decays. That Fermi type and Gamma-Teller type, that is also here, because the two particles, neutrino and electron, they go with these orbital angular momenta, but they still have their spin quantum number, which can combine to either s equal to 0 or s is equal to 1. So, s equal to 0 will be Fermi and s equal to 1 will be Gamma-Teller. So, you can have first forbidden Fermi transition or first forbidden Gamma-Teller transition, or second forbidden Fermi transition, or second forbidden gamma-tailor transition, and so on. So, this is how these transitions are classified in terms of L, small l, and in terms of the S of these two outgoing particles. So, what are the selection rules for these forbidden transitions? For example, take this case, first forbidden transition. So, L is equal to 1. So, that immediately tells that parity changes. Delta pi is 1 minus 1 to the power 1, that is. So, parity should change between the daughter nucleus and the parent nucleus. Now, angular momentum, if L is equal to 1 and S is equal to 0, that gives J is equal to 1. J I am writing for the total angular momentum of the two outgoing particles. So, that J is equal to 1, and if J is equal to 1, then delta I can be 0 or plus minus 1. We have just discussed this. If J is equal to 1, or two outgoing particles together with the daughter nucleus angular momentum, they should become equal to the angular momentum of the parent nucleus, and therefore, the change in angular momentum of nucleus as such, which we write delta I, should be 0 or plus minus 1. So, this is the selection rule for first forbidden Fermi transitions, because S is equal to 0, it is a Fermi transition, and first forbidden because L is equal to 1. So, that is the selection rule for first forbidden Fermi transitions. And first forbidden gamma-tailor transition, for that you will have L is equal to 1, first forbidden, and delta pi is of course 1, yes, it will change, and here S is equal to 1 for gamma-tailor, and L is equal to 1 and S equal to 1, they can combine to give a total angular momentum to these outgoing particles J, which can be 1 plus 1 can be 2 or 1 or 0, and this J will combine with the daughter nucleus angular momentum to give the parent nucleus angular momentum, and therefore, taking 1 by 1, 2 will give you a possible change 2, 1, 0 and so on, and 1 0 is already here. So, the total all these things will allow delta I 0 plus minus 1 or plus minus 2. So, these are the selection rules for first forbidden gamma-tailor transition. Similarly, you can work out for second forbidden Fermi and gamma-tailor transitions. Here L is equal to 2. So, parity will not change, and then 2 plus for Fermi you will combine S equal to 0, gamma-tailor you will combine S is equal to 1, and do similar analysis to get all these selection rules. Now, in terms of the wave functions that we had constructed, psi e 1 by root v 1 plus p dot r p e dot r by h cross, and then p e dot r I times over h cross square and so on. These are various degrees of approximations taken here. When I am taking just the first term, it corresponds to L equal to 0 allowed transitions. When I take this particular term and calculate that matrix element including this, it is bringing another momentum dependence, and also it is allowing L equal to 1 transitions. So, these are to be taken into account if we want to compare the experimental data with the theory for non-zero L. Non-zero L, you have to take these terms into account. So, maybe if it is if this is non-zero, then you will stop here. If this is also 0, then you will go here. If this is also 0, then you will go here. This way the expression has to be modified, and those calculations are finally they give what we call shape factor S, and this will depend on what L you are using, first forbidden or second forbidden or third forbidden, what kind of it is, gamma Teller, Fermi, and where you are stopping. So, all those things will decide the expression for this shape factor. This also is to be multiplied to that expression NP dP or NK dk. When that is included, and then the Fermi Curie plot again straightens and becomes linear. So, these are some of the things about angular momentum, parity, so on. The last thing I want to point out in this chapter is effect of neutrino mass. All these expressions are derived under the assumption that neutrino mass is 0, and in terms of mega electron volts, it is, even if it is there, it is very small and it seems reasonable. But then if we look at the shape of this energy spectrum, say Nk here and K here, and so this is a kind of shape at end point Q, when K is equal to Q, this whole probability becomes 0. Now, if you just look at this tail end, few tens of electron volts only. So, at this, in this region, the kinetic energy of the electron is close to the Q value, and that means the neutrino energy is close to 0, and therefore, at certain stage, as you are increasing kinetic energy, looking at higher kinetic energies, at certain stage very close to capital Q, it will so happen that the neutrino total energy will be comparable or comparable to its rest mass energy, if its rest mass energy itself is not 0. So, in this region where kinetic energy of the electron is very close to Q, the total energy available to neutrino is say few tens of electron volts. So, if it has got an rest mass, then you cannot use that expression which we used P nu times C as the neutrino energy. This we used, remember, when we were calculating this dN dEF, dN was written as some constant times Pe square, P nu square, dPe and dP nu over dEF. So, to get this expression dPe over dEF nu, so this we use this relation and wrote this as 1 by C. Now, this relation E nu is equal to P nu into C, that will not be valid if neutrino has a rest mass energy and the total energy available to neutrino is comparable to that. In that case, this will not be the case. So, in that case, one should write EF as m nu C square, and since the energy is small, so its kinetic energy is small, so one can write it as P nu square over 2 m nu. And if I differentiate, it is a neutrino energy, and the final energy which is available EF is m e C square m nu C square, and then plus kinetic energy of the electrons, and then this P nu square 2 m nu, and dEF will be P nu dP nu over m nu, okay, at a fixed electron kinetic energy. So, this, and therefore, this dP nu over dEF, this will be m nu over P nu. So, in place of this 1 by C, we will be having this 1 by P nu, and that will change the shape quite considerably. right, because when we write this thing here and use this Pe square and dPe is fine, then this is P nu square. If it is 1 by C, it is P nu square, and if it is this, it is P square P nu square multiplied by 1 by P nu. So, it is just P nu here. So, if I take this into consideration, rest mass into consideration, then this dN dF will be some constant times Pe square dPe, that will be there, and then you will have P nu. So, instead of P nu square, it has become P nu, and that will change the shape. P nu you can calculate. Now, you have these expressions, the kinetic energy P nu square over 2 m nu is Q minus K. Kinetic energy available to the neutrino is total energy available minus the kinetic energy taken away by the electron. So, this is P nu square. So, P nu will be 2 m nu and Q minus K square root of this. So, this factor will appear. So, if I write this expression for n k, which was some constant times square root of k plus 2 m c square, and then you had k plus m c square. This part is coming from Pe square dPe, Pe square dPe. So, this is giving me this part, and then multiplied by, now here is the difference. If it is m nu equal to 0, it is Q minus K square, and if m nu is not 0, then this whole thing will remain there. And this will be square root of Q minus K if m nu is not 0. So, where the deviation will start in the tail, that depends on what the neutrino mass is, 10 eV or 20 eV or by 30 eV, of course, by c square. So, but the at some stage this will start matching with better with the theory. So, now just to tell how different these two expressions can be, these two expressions can be quite different in this tail range, this Q by K square here and square root of Q minus K here. Just take this dN over dk. What does this give on this graph? dN by dk gives the slope. So, in this end region, how the slope is behaving, how this curve is reaching the horizontal axis. So, that slope will be given by dN by dk. Now, if I take the first expression where m nu is equal to 0, then differentiate with respect to k. So, you have let me write this whole thing as one part. So, this will be some constant times this square root k plus 2 m e c square and k plus m e c square, and then differentiation of this, which is 2 times q minus k and plus q minus k and into differentiation of that square bracket thing. Okay, just take this differentiation with respect to k. So, 2 factors, this is one factor, this is one factor. So, first I write this and differentiation of this, and then plus this factor differentiation of this. Now, at the end, at k equal to q, what happens? So, at k equal to q, if I look at these two terms, both of them are 0 because of this q minus k, present here, q minus k square. So, if you write capital K equal to q, this term will go to 0 and that will make this whole thing 0, and here it is q minus k. So, when you put k equal to capital Q, this also goes to 0. So, this whole thing goes to 0 at k equal to q. So, d and dk is 0. What does that mean? That means the curve nk curve approaches this k axis tangentially, like the one which is plotted here, roughly sketch. So, it is approaching it horizontally. On the other hand, if you take m nu not equal to 0, then you use another expression, m nu not equal to 0, then you are using this expressions. Once again take this as the first factor and this as the second factor. So, you have c times that first factor square root of k plus 2 m e c square and k plus m e c square, that is the first factor, and then differentiation of this second factor, and differentiation of this second factor is 1 over 2 square root of q minus k and then minus 1. Plus differentiation of this factor and multiply by square root of q minus k. Right. So, first keep this fixed and differentiate this, and then keep this fixed and differentiate that. Now, you put k equal to q, what happens? The second term will be 0, at k equal to q this factor is 0, and so the second term is 0. But the first term, when you put k equal to q, the first term, this term here k equal to q, this goes to infinity. So, if this m nu is not 0, however small, you will have this dn dk infinity. So, that would mean that if I look at this nk curve and then this portion, tail portion, that tail portion should meet the k axis perpendicularly. So, quite drastic change here. Where this change starts, and in an experiment, what is the resolution of that experiment, and whether this shape change can be seen or not, what kind of sensitivity is required, those things are there. But somewhere close to this q, it has to go in this fashion. So, by carefully studying the shape of energy spectrum of these beta decays, especially these allowed beta decays, one can try to get some kind of estimate of neutrino mass from these experiments. So, that is all about beta decays, and next time we will start something new.